Welcome to Module 8 of my online linear circuit analysis course. This module is titled More Complex Circuits. We say more complex in comparison to the single node pair and single loop types that we looked at in the previous module. So what types of problems specifically are we going to address here? Circuits that are a bit more complex than a single node pair or a single loop, perhaps one with 2 to 3 loops or 2 different sets of parallel branches. We'll learn how to solve such circuits by using series and parallel equivalencies to simplify the topology, and then some combination of basic circuit laws, KVL, KCL, in order to generate a closed form solution. Soon, we're going to discuss more formal methods to solve these types of problems, such as nodal analysis. However, these do present some overhead. As such, I think it's very important to learn how to solve these slightly more complex problems using your basic intuition. It's going to come in really handy for classes like electronics. But let's go ahead and start off by jumping into an example.
So what if we have a circuit that's more complex than a single loop or a single node pair? Those being the two examples that we discussed in the previous lecture. What we can do is we can use series and parallel combinations to simplify the circuit, and then take those values to solve the original. Now we could go through and define a step-by-step process. However, like many aspects of this course, I feel like an example is the best way to demonstrate. So let's take a look at this example here. We have a somewhat complex circuit, more complex than what we saw in the previous lecture. Topologies defined right here, values defined over here. Now the first question I would ask is this a single loop? Well, obviously not. We can see 2 loops. And is this a single node pair? No, not a single node pair. Okay. So we can't use or apply either one of the methods from the previous lecture directly. We see we have 2 loops here. Let's find a way to simplify. Let's try to collapse that second loop using equivalent impedances. Now what we're doing is we're taking all this area that's highlighted in yellow, and we are going to represent it as a single resistor named R equivalent. Now what's going to be the value for that resistor? That's going to be demonstrated by the equation over here. Now, where does this equation come from? It reflects the fact that we have a resistor R2 in parallel with essentially the series combo of these 3 together. So R2 is here, and then this represents the series combo of R3, R4, and R5. Hence that equation. Now R3 plus R4 plus R5 gives us 1250. You can see that up here, and we drag that value down here. And then 500 is the R2. So we calculate the parallel equivalent value for 500 and a 1250 ohm resistor, which gives us 357.14 ohms. Now we have a single loop. We want to solve for the current IS right here. This requires us, as usual, to define KVL for the single loop. This is similar to the process that we used in the previous lecture to solve a single loop circuit. Now let's talk briefly about what happens to the rest of the values that used to be over here. Those values are no longer observable. So for example, we can no longer observe V45. We can also no longer observe what I would call current I45. Those values are no longer observable in our simplified circuit, but some values are. For example, IS, as we defined it below, is the same as IS defined up here, and a voltage like V25 would also be observable in both the circuits, even though we're changing what resistance we see placed in that spot. In reality, that resistance is not changing. It has always been the equivalent resistance of all those together. So that's one word that we should become familiar with, is this observability. Okay, so we have this single loop. We want to solve for the current IS, and that requires us, as usual, to define KVL for that loop. So that's what we've done over here. We're using VS1 as our referential positive polarity, which gives us a KVL of VS1 plus VS6 minus V12 minus V25. If you have questions about that and how to apply KVL, I recommend you look back at some of the earlier lectures. Okay, so in this step right here, what we've done is we've grouped together the two sources, and we've replaced V12 and V25 with their Ohm's law-based equivalences, both of which are then in turn dependent on IS, right? There's only one loop flowing, only one current flowing through this loop. We can then group together our resistances. We already have our voltage sources grouped together, and we can solve for IS, and that is what is shown right here. VS1 over VS6, VS1 plus VS6 over R1 plus R equivalent. We already have those values, and we end up with IS equals 10.9 milliamps. All right. So now what we can do is we can calculate the voltages that are present in the simplified circuit, mainly V12 and V25. We cannot, however, calculate any of the voltages associated with nodes 3 and 4 because they are unobservable in this circuit up above. So we calculate V12 as IS times R1. We calculate V25 as IS times R equivalent, giving us the values of 1.093 and 3.906. Note that we can check our work along the way. So what we see is that 1.09 plus 3.906 gives us 5 volts, as we would expect from KVL. If we take a look at the circuit up here, we know that these together should equal 5 volts. One is 3 and one is 2 volts. And so therefore, in the same vein, we expect the sum of the voltages across those two, V12 plus V25, to also equal 5 volts, and it does. Now, why do you want to perform checks like this along the way? It's just giving you information that you already know. Because if you end up with a discrepancy, it can be a great opportunity to fix it before you proceed further and base more of your work off of an incorrect value, which then just requires more time and effort in order to fix. So now we've calculated everything we can from the simplified circuit right here, right? We've gotten everything we can out of this. Now we want to go back to solving for some of those values from the original circuit. So what we're going to do is we're going to return to our original circuit, but this time we are going to place sources for the values that we know. Now, I saw this method in a textbook. I'm not sure I'm going to use it in other problems because replacing some of the resistances with a voltage source can lead to some unfortunate, or let's say undesirable, assumptions. You can also do the exact same thing without using these sources by simply just saying we know what V25 is and we know what IS is. Okay, so take this how you will, this version of the circuit over here with the some of the elements replaced with sources. Perhaps we should just use this version over here with the knowns assumed to be known. All right. Now, regardless of which version of this circuit that you use, let's say the one with the sources or the one without, okay, the same assumptions or the same observations can be made. First is that we have some values that are known. We know what the voltage is here, and we know what the current is here. I'm not sure why I call this iCalc On the right hand side, it was originally just IS, so I'll put that there. And we know V25. So what we can see is that given the information we know, we can easily solve for I23 and then all of the voltages along that path given the information that we know. So this is I23 right here. It's the current that flows along this whole secondary path. We already know what V25 is because we calculated that as 3.906 volts. And we really don't need to use anything associated with nodes 1 and 6 anymore, so that's the reason why they are left off. So now what we're going to do is solve for the remaining values. I'm going to replace all these I25s with I23. I'm not sure why I changed what I was using. Then the remaining steps are relatively straightforward. We know what V25 is, and we know what the combined resistance of all three of these elements are, and that allows us to calculate I23. This makes sense, right? Because if we take a look, we have three resistors. We know the voltage across them, so therefore we can calculate the current flowing through them, and that is I23 is equal to I34 is equal to I45, right? The current through all three of those elements will be equal as dictated by KCL. And so when we solve that equation, we end up with 3.12 milliamps, and then we simply apply Ohm's law 3 times, and that gives us 0.624 volts, 0.156 volts, and 3.12 volts, which essentially solves our quote-unquote more complex circuit. Now, how did we do that? Just a quick recap. We started off with a relatively more complex circuit. We collapsed this piece into an equivalent resistance, REQ, placed where R2 is now. Solved for whatever values we could, mainly IS and V25. We then copied those known values over to our original circuit, which is still shown here, and then used those, specifically we used V25, in order to calculate the remaining unknown values. The next section is labeled even more complex circuits. Now, what does that mean? What if it seems that you cannot collapse or simplify your circuit sufficiently? Theoretically, you should always be able to perform the simplification, but what if you can't do it? You can't make the simplification, or you can't practically make the simplification to a single loop or a single node pair. There's really no easy answer here, but I can suggest several steps. Now, there is one alternative that we haven't learned yet, which is nodal or mesh analysis, which can provide a pretty good route to solve these types of problems, but we're going to assume we don't know that yet. So the steps are, first, we're going to label all of our electrically independent nodes in unique currents. Step 2, we're going to write out all or several equations that we know. Do we see any relatively easy path to solve, even just for one unknown value? If so, great. Do that. I'm going to say get rid of R and say may be done, because I did say you could solve for just one value, so you could be done. But if you get to a point where you can no longer do this, where you no longer see an easy path to solve using those equations, then you move on to identifying a known voltage or current from which you may expand outwards, calculating other unknown values. Now, this is a very heuristic process, because it all boils down to me saying one thing, which is solve the algebra. Because the circuit we translate that to a set of algebraic expressions using the physics and the electrical circuit theory. And solving the circuit is really just a matter of solving that system of equations. And that again ties us back to nodal or mesh analysis. So that's what we're trying to do here. If you're very good with algebra, then that will help you with a lot of these types of problems. And if you're not so good with algebra, then you may perhaps have a little bit of a more difficult time. This whole lecture is really, in many ways, a stopgap between the last one and a future lecture where we talk about nodal and mesh analysis. However, that being said, I still think there's some important nuggets to be taken away from this. So what if you were given a circuit like that below? So let's take a look at what we have here. It has a current source and a couple of resistors, as well as a voltage source. Now, it's not a single loop, it's not a single node pair. What's one way that we could solve? And what I've done is I've labeled some steps 1 through 7. 2, 3, 4, etc. So let's look at how we may do this. So first, we know that IS equals IS. Obviously, it's a source that's defined. KCL tells us that IA, as defined here, equals IS. Ohm's law tells us that VA, as defined below, is equal to RA times IS because the current's flowing through that resistor RA. We can then split IA into IB plus IC via KCL, where IB is defined here and IC is defined here. Ohm's law will tell us that VB equals IB times RB, and KVL / Ohm's law tells us that IC is equal to VB minus VS over RC. Lastly, we can combine steps 3 through 6 to create this expression here, which says that IA is equal to VB over RB, that's taken from the green above, plus VB minus VS over RC, and that's taken from the red highlight above. Now, what did we do here? We used the one known value, which is IS. Well, we have another one, which is VS, but we used one of the known values, and we expanded, as this gray arrow shows, outward and around to use that to calculate the other values. Again, this is a pretty heuristic process, so it may be difficult for some of you to repeat this for more generalized circuits. I do think practicing this method, however, is pretty advantageous. It provides a lot of benefits later on when you're in a course like electronics and you need to solve or to analyze pieces, sub-circuits within a larger circuit without relying on nodal or mesh analysis. You just need a quick and easy way to solve a sub-circuit. So like I've done in many parts of this class, we're going to use an example to demonstrate. So we want to solve for VS, which is this source right here, and we do not know the voltage which it generates. We know all these resistance values. We have a second known voltage source, and then we know what the voltage is across that 1 kilo ohm resistor. This output voltage is 4 volts. So how do we solve this? We're taking these steps largely from the advice that I gave above. We want to label all the nodes and parallel currents. That's done. Nodes A, B, C, D, E, F. I didn't really have a need to label any parallel currents. What do I mean by that? So normally, let's say we have a circuit looks like this. And this is node X, Y, and Z. Actually, I take that back. These are electrically the same point. So these are both node X and we have node Z, but two separate resistors. So this current we would call IXZ. Now, if we didn't have two parallel paths, we could also label this using the double subscript notation IXZ. But since they are parallel paths, we'll need to give them different names. Normally what we'll do is we'll call one of them prime. So that's what I mean. I mean, that's not a factor in this problem, but that's what I mean when I say we have to appropriately label parallel currents, because we can't rely on the double script notation for those. Okay, step 2. What known state value is closest to our desired unknown? All right. So our desired unknown is the Vs, and the closest known value is the 6 volts, VBC. Can we solve, sorry, that's not save, that should be solve. Can we solve for any neighboring values? In other words, can we use that VBC in order to solve for the value next to it? There's really not any practical way of using that piece of information by itself. So, hence why I put nothing easy. So let's move on. Now let's move on to the other known value, which is IFD, right here. Can we solve for any neighboring values? Again, we're using this method where we're expanding outward. So all we can really derive from IFD are these two equations. We know that IFD, which is 2 milliamps, is equal to IDC plus IDE. That's just applying KCL at node D. And we know that ICB is equal to IDC, and that's just applying KCL at node C. So really all we can do is take this current and split it into two different pieces, but we don't know what ratio they have with respect to one another. We don't know if IDC is equal to IDE. Do they have a 2-to-1 ratio? It doesn't give us much information, unfortunately. All right. So now let's keep moving on. We started off here, right? We tried that. We couldn't really expand out. Then we moved to this. Couldn't really expand out. Now we're at our last known value, the furthest from our unknown, which is the V out equals 4 volts. Hopefully that can help us. So we're going to move on to V out equals 4 volts. Can we solve for any neighboring values? We can. This one provides us a more practical path. IEF would be equal to V out divided by 1 kilo ohm. That's simply solving for the current flowing downward along that branch. And we see that's 4 milliamps. We can then see that IDE is equal to IEF. That's just applying KCL at node E. There's one branch coming in, one branch heading out. We can also see that ICD is equal to IDE minus 2 milliamps. Now, where does this come from? This comes from this equation up here, right? We drag that down here, and we see that ICD is equal to IDE minus 2 milliamps. So that comes from applying KCL at node D. And so therefore we see that ICD is equal to 2 milliamps. Then we already know that IBC is equal to ICD. That equals 2 milliamps. That's again taken from this right here. And so we have a lot of information. That was actually very helpful. Okay, but we can't expand any further. Okay, once we get to node B, we really can't expand out any further. So what's next? Let's review what we know. So what I did was I redrew the circuit here, but including now our known values. So we always knew this source. We always knew this source. We didn't previously know the voltage here or the current, but now we do. We know that VCD is equal to ICD times 3 kilo ohms, which is 6 volts. That's highlighted in the blue. We also know the voltage right here, highlighted in the red. We know that VDE is equal to IDE times 2 kilo ohms, which gives us 8 volts. So, and we already knew what was highlighted in the gray. So what we have is essentially the known voltage or current for each one of the shaded or the highlighted yellow, blue, red, green, or gray elements. So we can use this now as a tool to analyze our options. And we see one option, the loop BCDEF, which would essentially look like this. So BCDEF. So it would look like that. Okay, that loop contains only one unknown voltage, and that would be the voltage across that guy. So we could solve for VBF, again that one, using KVL. So what we've done is we've written out our KVL expression, and I did it using the double subscript notation, VBC plus VCD, so on, so on, and so on. This work right here simply just shows that it ends up equaling 0, which is what we want because it equals 0 on the other side. VBC can be broken into VB minus VC. VCD can be broken down to VC minus VD, and then so on and so on. You can see that the double subscript notation, if KVL is applied properly, cancels itself out. So we plug in the values that we know. We isolate the only value that we don't know, which is VFB or VBF. I flip the direction of the subscripts going from the top to the bottom. So we know that VFB is equal to negative VBF. So making that flip, what we see is that VBF is equal to 6 plus 6 plus 8 plus 4, or 24 volts. So all these elements right here, their voltages together give us 24 volts. And then Ohm's law will allow us to expand outward and solve for IBF. We know now we have the voltage across that branch, so we can solve for the current through that branch. And so IBF is equal to VBF divided by 12K, again because it's a 12K resistor right here. And that gives us 2 milliamps. And now we can continue to expand to the left using KCL. And this is applying KCL at node B. We can calculate IAB as the sum of IBC and IBF, both of which we already know. 2 plus 2 gives us 4 milliamps. And finally, we are left with one loop with one unknown, right? Sorry, one second. So we're left with one loop with one unknown, which we've drawn the loop right here. We know that VBF is equal to 24 volts. And we also know the current IAB, right? We know the current flowing in this direction. We calculated it actually right up here. We know that's equal to 4 milliamps. And so therefore, we can calculate the voltage across that element, which will give us VAF, negative 12 volts. And then we can apply KVL to that whole loop. VAB, which is equal to negative VAS, plus VBF plus VFA equals 0. We simply plug in the known values and we solve to get 36 volts. Now, again, I know this process may be relatively difficult to recreate. However, I think it's a great practice problem. I think it's a great way to become more familiar with solving more complex circuits, which require a little bit more intuition with respect to both circuit analysis as well as the algebra. So there's value there. Since this example is a little bit more complicated, I thought it might be nice for us to use a simulation tool in order to check our answer. So what I've done is I've loaded up LT-Spice here. I'm not going to talk too much about the differences between different simulation packages and what they mean. LT-Spice is a pretty safe, good choice for simple problems. Plus, I'm using my Mac right now, and it's one of the ones that provides a Mac version. Although I will say that the PC version is a lot better. So if you have a PC, I recommend you do the circuit simulation on the PC. All right, so I've downloaded LT Spice. It's free, available online, installed it, and now what we're going to do is go ahead and start a new blank schematic. And this is really not meant to be a tutorial of LT Spice. I'm just going to quickly breeze through things in order to verify the answer we calculated previously. Okay, so a couple things here. I normally like to turn on the grid. I like the dots, so I'll leave those there. And let's go ahead and place our components first. Each time I bring this menu up, I'm just right-clicking. And again, note that the PC version is a little bit different. There's a menu, I think, at the top. Okay, so we want to download, or not download, we want to place some components. So I'm going to go here and let's pick a voltage source. I can use Control R to rotate it to give me the appropriate direction. So that's going to be our VS. This is going to be the 6 volt voltage source. Okay, that's all the voltage sources that we need. Right click again. Let's go ahead and go with some resistors. Again, pretty easy to choose those here. Using Control R to rotate, this is going to be our 3 kilo ohm resistor. This is going to be our other 3 kilo ohm resistor. This is going to be 12 kilo ohms. Our current source is going to go here, and then lastly we'll have what I'll call R out. Okay, so that should be all the resistors we need. We still need a current source, so go to parts and we'll find current. Got to rotate it the correct way. Okay, and then that's all of our components. Next thing that we're going to need to do is to connect everything. So I'm going to choose wires here. Connect everything up the way that we want it. If you're not familiar with how to use this type of simulation software, there's tons of great tutorials available online. I think I have one on my channel, although at the moment I'm not 100% sure. I can't remember if I put that up yet. All right, so we've connected all of our wires. We will need a ground. So I'm going to go here to net name, and we can actually choose ground as one of the options. And I'm just going to ground anywhere down here. Now the ground, we don't often specifically show where that is in our homework problems, but we assume that node F was our reference node because our voltages were defined with respect to that. So I'm going to place my ground there. Now let's do the names. So this right here. So in order to define the names, you have to right click on the actual name. So this is VS. I'm going to call this, I'll use double subscript notation. This is V. And there's a problem with my schematic. I left out one of the resistors. This is VBC. And I left out the resistor right here. So what I am going to do is go to edit, and I am going to go to move, and I'm going to move a lot of this stuff to the right. I'll delete. So again, edit, delete some of these wires. Okay. And I have to move some stuff over. So again, edit, move, gonna move. Well, I can leave this right here. Move this source over. And then now I'll need one additional resistor because I forgot that resistor there. Okay, let's go to res. Okay, so this will be the 2 kilo ohm resistor. All right, so now let's connect the wires back up. Well, let me move this back to the right spot. Okay, now let's connect the wires back up. Okay. So now we have all the components properly placed. Let's go back to the naming. So I'm going to name this RCD because it's between nodes C and D. I'm going to name this one over here RDE because it's between nodes D and E. We didn't really give these good names previously. This is REF. I'm going to call this IFD because it flows between nodes F and D. This is RBF because it's between nodes B and F. And this is RGB let's see, AF, because it's between nodes A and F. Now we've done the names, we haven't done the values. To do the values, we simply right click on the component itself. So this is 3000 ohms. This we solved as 36 volts. This we are given as 6 volts. This we know is 3000 ohms. This, sorry, could I right click on this one, is 2000 ohms. This has a value of 2 milliamps. Again, I'm just right clicking on the component itself. This has a resistance of 12,000 ohms. And then lastly, this one over here has a value of 1,000 ohms. Now, what I should be able to do is run this circuit and observe a 4 volt difference across the REF. Let's try running. No analysis command found. That's true because we have not set our simulation profile. This is a lot easier on the PC version, but here for Mac, what we're going to do is go to draft. We're going to go to spice directive, and we can just type in a pretty simple comment, which is transient, 10 milliseconds, doesn't really matter. Put that down there, and now when we run, it should give us something. And I think I forgot the period. All right, let's try that one more time. I'm just hitting the running man up here, by the way, when it's time to run. Okay, and it worked. Great. But there's nothing showing up on the screen because we haven't placed any probes yet. So what I can do is just go over here, and it automatically turns into the probe tool. And I'm going to click right here at the top of REF. And that should give me the value VEF, or what we call V out. And what you can see is we get a value of 4 volts, which is what we would expect for this circuit. And so in that regard, we've used LT-Spice to demonstrate that the answer we acquired previously was correct.
So that marks the end of this module. It's a great bridge between the simpler circuits, the single node pairs and the single loops that we learned about last time, and the increasingly complex circuits that we're going to see in the upcoming lessons, 3, 4, 5 plus node circuits. I'm sure many of you, when you learn about nodal and mesh analysis in these upcoming lectures, are going to say, well, hey, this is a much better approach because it's so methodical for solving these types of circuits, and it does have its place where it is optimal. However, I don't want to neglect this lecture too much, because when you're in electronics class and you're dealing with some closed loop op-amp problem and you really quickly need to solve for the voltage across that feedback branch, sometimes doing nodal or mesh analysis can be less than optimal. It can have too much overhead and take up too much time. And that's the case where you think back to this lecture and say, how can I quickly use KCL, KVL, and similar laws together in order to solve for the value that I need?